meeting. So I have a bunch of journals here. Okay, let's see, why don't I just pass them out at random? Because some are better than others. Okay, first one, who wants it? 1, 2, 3, 4, 5. Okay, 2 more. Okay. Okay, now, you had a question.
I just think the second problem is very similar to what you taught in the last class.
The second problem is similar. Yeah, what it says is that when you do exercise 12, which you do in part 1, and you have the solutions manual so you can copy it, although that's not the intention. The intention is to do it on your own and then use the solutions manual to answer your questions. But what you turn in the right answer. Okay, now, number 2 says that in exercise 12 there's an equation 4, and it asks you to show that that equation, that for the omega hat of S, can be written as a product of 2 terms, one of which is the Laplace-Dirichlet transform of the waiting time you would find in an ordinary MG1Q that had no vacations. In other words, the Pollaczek-Hinchen transform. And the other is another piece. And when you factor out the Pollaczek-Hinchen transform, you will recognize that what that other piece is it is the transform of the distribution function of the forward recurrence time of a renewal process in which the renewals, the intervals, are vacations. So that means that since the transform of the waiting time in the vacation model is a product of transforms, that means that the distribution of the waiting time is a sum, has the same distribution as a sum of 2 independent random variables, one of which is distributed just like the ordinary waiting time in an ordinary MG1Q in which there are no vacations, and the other of which is distributed like the forward recurrence time in a renewal process in which the renewals are the vacations. Now that's just algebra, and it doesn't mean that an individual customer sees 2 pieces to make up his waiting time, one having transform omega and the other having transform v tilde. It does not mean that. It doesn't say that. It simply says that in distribution, the distribution of the waiting time in this model is the same as the distribution that you would get by adding these 2 random variables. It's very surprising.
Yes, according in comparison with what you taught last time, they are opposite. The waiting time, like the batch arrival, you specify 2. Why is W1, why is W2? I think the problem is very similar to this one.
No, actually, they're very different. You're talking about the batch arrivals. Now, in batch arrivals, the problem is simple, because with the batch arrival, what you say is that if you look at an individual customer, then you can break his waiting time down into 2 pieces. First, how long it takes until the first customer in his batch begins service, and then how much time he waits until the customers in front of him in his batch get served. So each customer has a waiting time that's the sum of 2 pieces, until his batch starts and then until he starts. Of course, if he's the first person in his batch, then the second piece is 0. Now that's what's called a sample path argument, in the sense that if I were to draw, well, I haven't really described the sample path, but what it means is that the pieces that fit in the formula, the 2 random variables you add, each customer sees his waiting time as a sum of those 2 pieces. Yeah. So although the arithmetic may be complicated or tricky, there's nothing theoretically interesting about that. Actually, there is something theoretically interesting, which is that the discrete version of the forward recurrence time happens to be in there. in a way that once you recognize it, it's obvious that it's there, but it's easy not to recognize. A lot of people have made the mistake of not recognizing it. And if you make that mistake, unlike most mistakes in queuing theory, it doesn't detect itself. The answer still makes sense, but it's not right. Now, in the vacation model is conceptually different, because in the vacation model, you get this decomposition by solving the problem and then noting that the answer, when you get the transform of the answer, that it's a product of two transforms, each of which you can identify. But that does not mean that each individual customer has his waiting time broken up into two pieces, which can be identified as what he would wait if there were no vacations and how long he waits for the vacation to end.
Yes, certainly there are two terms. One is as usual, as the no vacation, the waiting time. Another is the how long the customer waited in the vacation.
All right, that's the answer. The answer says that the Laplace-Dirichlet transform of the distribution function of the waiting times in the vacation model can be written this way. You didn't start writing it this way. What you did is you embedded a chain at the service completion epochs, and then you went through an analysis that was analogous to what you did with MG1, but the details are different. And when you get done, you get some expression. Now, when you get that expression, it turns out, this is what you're supposed to verify, that that expression can be factored into two pieces.
Yes.
This piece is exactly the Pawlicek-Kinchin formula for the same model if there were no vacations. And this piece can be identified, because it has the same form, as what you would get if you ask this question. Suppose you have a renewal process in which the renewals are the vacations. So this is vacation 1, vacation 2, vacation 3, and so on. Now, you don't have such a renewal process because the vacations are separated by times in which the server is working. But suppose you had such a renewal process, and then you said, okay, I'm going to interrupt this process at random and ask for the remainder of that. Now, if I took the Laplace-Dirichlet transform of the distribution function of this remainder, then its formula would be exactly this. Now, there's no reason for that, or no obvious reason. That's just the way it turns out. But since that's true, what that means is that if the transform is a product of two other transforms, then that means that the distribution that this transform specifies is the same as the distribution I would get if I took the convolution of the distribution that this transform specifies with the distribution that this transform specifies. So that means that the distribution of the waiting times in the vacation model is the same as the sum, as the same distribution as the sum of two random variables, one of which is how long you wait in exactly the same queuing model but without vacations, and the other, how long you would wait until the next renewal if you interrupted a renewal process at random in which the renewal intervals are the vacations. But that does not mean that an individual customer, when he comes in, can have his waiting time broken down into two independent pieces, one of which is what there would be if there were no vacations, and the other being a partial vacation. That's not true. Every customer either arrives during a vacation, in which case he waits a partial vacation plus some other stuff, or he arrives when the server is working, in which case the vacation doesn't affect his waiting time, except to the extent that it may have affected the queue in front of him, the size of the queue in front of him. So you cannot break down an individual customer's waiting time into a sum of two pieces. But the distribution of his waiting time is the same as the distribution of the sum of two independent random variables, one of which is generated by this transform, and the other of which is generated by this transform.
In this case, you just ask us to calculate the transformation of the forward recurrency of the indication and in comparison with the original result we got.
That's right. I'm just asking you to prove that it's true. The proof that it's true is easy because once you have this answer, which is already given in the problem, then it's just a matter of algebra to break it into two pieces, one of which is this and one of which is that. So that proves it. So there's no doubt that it's true. But it's very surprising because it's not true on a sample path or customer by customer basis. It's only true on an overall basis. In fact, it's so surprising you might not believe it. But if you were to look at part 3, for example, this may be the next homework problem. Part 3 asks you for a specific case. It says, suppose the service times are exponentially distributed and the vacation lengths are constant. Okay, now in that case, it's easy to find the distribution of the waiting times in the vacation model. Because what the formula tells you is, well, this is the waiting times in ordinary MM1, which you already know. And this is just the forward recurrence time of a renewal process in which the renewals are constant, which means that the length of the forward recurrence time, or the forward recurrence time, is uniformly distributed, because this is a particularly simple case. So in that case, you can actually do the arithmetic because you can take the convolution of that with that in probability space, not in transform space, and that will give you the inverse of that. So you can actually calculate it. It's very easy. When you calculate it, you get an answer, and then using that answer, you can find this probability. Because once you have this answer, you have the distribution, so therefore you can calculate the probability of lying in any interval. Now, if you were to, this could be the assignment. I could say, okay, now, take the simulation you have that simulates MG1 and adjust it so that now it simulates MG1 with vacations. It's not hard. And then run the simulation for that model and then compare the measured waiting time distribution with the distribution computed this way. And of course, you'll see they're very close. But it's surprising. It's amazing. And it's very important because what it shows is that, as we'll see later, that in more complicated models, polling models, what that means is that there's a separation between two pieces. One piece has to do only with the queue, the queuing effects, and nothing to do with when the server is serving the other queues. And the other piece has to do only when it's serving the other queues and nothing to do with the target queue. So it separates the pieces and allows you to consider them independently, even though in terms of the way they affect an individual customer, they're all connected, they're interleaved. So it's an amazing mathematical fact, and it's a very practical simplification, and it allows you to solve polling models, which is what we're getting to. You don't look convinced. The trouble,
assume it's very simple model, like the batch, right? Very similar.
Well, it's a simple model to envision, but the analysis is simple because you just did it. But the reasoning behind the analysis, the mistake you're making is you're trying to understand what this means. And I'm saying that maybe it doesn't mean anything except that it's a fact. It doesn't mean, well, it doesn't mean that just because a waiting time has a certain distribution, that doesn't mean that for the individual customer, his actual waiting time must correspond to that. Let me put it another way. There might be lots of ways that I could generate a particular distribution. That is, maybe I could take this distribution and say that that's exactly the same as what I would get if I sampled from this thing and squared it and then divided by some other random variable. No reason it might just turn out to have the same distribution. So just because you have a distribution, it doesn't mean that there is a unique way that it arose. In this case, you have the distribution, and it can be shown to be equal to some other distribution that's obtained a different way. The fact that that's true is easy because it's just algebra. But the reason that it's true is not at all clear. It just happens that way. It's not true because you can break down an individual customer and look at his waiting time as represented by some of these pieces, although in the batch arrival model you can. That's why batch arrival is not a big deal. It's straightforward analysis. So this is a very unusual result. Very important. It's really very neat because it has the things that everybody wants. On the one hand, it's mathematically interesting because there are lots of generalizations of this. And on the other hand, it's actually useful. And so when you can find something that's interesting for its own sake and useful, then you're in heaven. That's what else is there in life?
As to the problem F, number F, it seems to me that there is you needn't have this condition that the vacation lengths are independent of arrival process. According to your definitions, whenever if the server is in vacation, if there is no customer arrival, it's continuous vacation.
Right.
Which means every customer has to wait. In many cases, since the probability for the customer arrives at the same time as the server started to serve is 0.
Okay. In part F, you're right. If the vacation lengths are independent of the arrival process, then every customer has to wait. But let me give an example in which the vacation lengths are not independent of the arrival process. Suppose I had what's called an N policy. Now, in an N policy, what that means is that, it's called N policy. This is standard stuff now. In the N policy, the server goes on vacation until the nth customer arrives. And as soon as customer number N arrives, that triggers the end of the vacation. And the server immediately starts to work. That's a fair model. You say that when the server becomes idle, it goes on vacation until 4 customers are present. And when the 4th customer comes, the server goes back and starts its work. That's an example of a vacation model. But in that case, the vacations and the arrival process are not independent because the arrival process triggers the end of the vacation. Okay, now, suppose that I took the special case in which n is equal to 1. If n is equal to 1, then the server always returns immediately when the first customer arrives. Now, in that case, the vacation model reduces to the ordinary MG1 without vacations. Because what's the difference when there's nobody waiting, whether the server's on vacation or the server is ready to work? If when nobody's waiting, the server goes on vacation, but it returns immediately if someone arrives, then the two models are going to produce the same waiting time. If they produce the same waiting time, then the N policy with n is equal to 1 can result in a case in which the customer does not wait, because it's ordinary MG1, and in ordinary MG1, not everybody waits. So here's an example of a vacation model in which the end of the vacation is triggered by an arrival, in this case the first arrival. And in that case, that arrival does not wait. And so therefore the probability of waiting would not be 1. It would in fact be rho, as we already know for ordinary MG1. That's actually, that element is brought out in part H, where it says, suppose that f of z equals z to the j. Now, f of z is the generating function of the number of customers that arrive during a vacation. So if it's z to the j, that means that with probability 1, the number of customers present when the vacation ends is exactly j. And the only way that can happen is if the server then returns immediately with the jth arrival. Okay, so I should have used n instead of j, because then I could have used the words n policy. Remember, this book was written a long time ago, and it's only, well, with hindsight, I can see how things come together that I didn't see at the time. Okay, now that says, it asks you whether equation 4 is correct when j equals 1, 2, 3, and 4. Now, 4 is based on the fact, on the assumption that the vacation lengths are independent of the arrival process. And the answer is no, it's not correct, unless j happens to equal 1. And in that case, the vacation model reduces to the ordinary MG1 model. This is a mistake that many people have made lots of times. In fact, even today. In fact, just within a month, I was a reader on a dissertation in which somebody was writing a PhD dissertation about polling models. And there was an N policy involved in the polling model. So it was more complicated than a vacation model, but it had the same ideas embedded in it. And the person had made exactly that mistake. Of course, he was saved because the independence, see this, the version of this with generating functions is true whether they're independent or not. And, well, I'll put it another way. The expected value of a sum is the sum of the expected values whether or not the random variables are independent. So in the N policy, if you go through this analysis, it's easy to get the expected value, but it's hard to get the distribution. So the dependence does not affect expected value calculations, but it does affect distributions for moments beyond expected value. There's a lot to this, so the fact that you don't understand it should not bother you if you understand it at a deep level. In fact, the fact that you realize you don't understand it at a deep level is a good sign, because if you didn't realize that, then you really wouldn't understand that you don't understand it, if you understand what I mean. Okay, so all your observations are yeah, they're to the point. But if you actually wrote a simulation to simulate part 3 in the homework, if you didn't make a mistake in the simulation, you would find good agreement. Okay? Any other questions about the homework? How many people have done it? So when should I make this due? I mean, the homework is not hard. It's strange that it's true, but it's not hard to do, because all you have to do is formulate the problem and then follow the rules, and it all drops out. It's just arithmetic once you state the problem properly. Okay, let me make it nominally due in a week. Okay, because I know, psychology being what it is, that if you don't make a due date, then nobody does it. They say, well, it's not going to be due without some interval from the time he says it's due until it is due, so I'll wait until then, and then I have that little interval. In my other class, I have this homework problem, which I told the students was going to take a lot of time because it involved running a simulation and plotting some graphs. And then I was out of town, so for that reason I actually gave them an extra week to work on the problem. So they've had at least 3 weeks to work on the problem. It's due today. And just before I got here, I got 3 telephone calls from students asking me questions equivalent to, what does X mean? So obviously they say, okay, it's due at 4 o'clock. And so what I'll do is I'll start at noon, and I got 4 hours. Should be easy, even though I've already had 3 weeks. And I told them it's going to take you a long time. Hopeless. Okay, so this is due a week from today. Any other questions? Okay, so let me see if I can remember where we were. Yeah, one of the things we talked about was the MG1K. And I'd like to take a look at exercise number 21. And I'm going to pass out a homework. This is homework 4 in an earlier version of the course. And at the top it says, not for credit, do not hand in. So I'm going to discuss it now, but you don't have to do this to hand in. Pass us down. So we're discussing MG1K, which actually this is just a name. The way I represented it in the book was to say we have a single server and we have n waiting positions. So there's a capacity of n plus 1. And customers, of course, arrive according to a Poisson process. And the service time distribution function is general. And we assume that when a customer arrives, if all the waiting positions are occupied, then he's a lost customer, a lost call. And if not, then he either enters service immediately if the server is available, or he enters the waiting room and he waits until served. And one of the things you're interested in here is pi sub n plus 1, which is the probability from the viewpoint of the arriving customer that when he arrives he finds n plus 1 customers in front of him. That means that all the waiting positions are occupied, so this is going to be the fraction of customers who are lost. And I discussed, I think it was in the last class, how you actually calculate this thing. Okay, now this homework that you don't have to hand in says, do exercise 21A and B on page 238. So there's exercise 21. It asks you to do A and B. Of course, you have the solutions manual, so I'm not going to bother to do it. You can just look it up. It's no big deal. Okay, now if you do that, what it asks you to prove, one of the things it asks you to do is this. It says that pi sub n plus 1 is given by the following form. Pi 0 hat plus a minus 1 sum nu equals 0 to n pi nu hat divided by pi 0 hat plus a times the sum from nu equals 0 to n of pi nu hat. Now, in this formula, this is the probability that you want to calculate. And the corresponding pi's with the hats are for the same model except with an infinite number of waiting positions. Remember that the probabilities for this model are similar to the probabilities for the cases n goes to infinity, except that they're truncated, which means that up to a certain point the probabilities are proportional. So here the argument goes, suppose you had actually solved the problem in which n is infinity and you had those probabilities. Then you could put them in this formula and you could calculate pi sub n plus 1. Okay, now, that means this can be rewritten as follows. So this is in the book. This is exercise 21B asks you to prove this fact. Now that can be written as follows. If A is the offered load, then in the case where I have an infinite number of waiting positions, pi 0 is the probability that an arriving customer finds the system empty. So that's 1 minus A, regardless of what the service time distribution is. We already know that, or 1 minus rho. A and rho are the same in the case of one server. So that's going to be 1 minus A plus A minus 1 And this sum from 0 to n is the same thing as 1 minus the sum from n plus 1 to infinity. And I've written that this way. I'm going to call the sum from n plus 1 to infinity pi sub n plus 1 infinity. So I don't have to keep writing sums all the time. And that's defined in the handout, in the problem. And the denominator is 1 minus a plus a times 1 minus pi sub n plus 1 infinity. Okay, now that implies the following by ordinary algebra. All I do is solve this for pi sub n plus 1 infinity in terms of pi sub n plus 1. And what you get is this result, which is what the homework asks you to prove. It asks you to prove that pi sub n plus 1 infinity is equal to pi sub n plus 1 divided by 1 minus a, 1 minus pi sub n plus 1. And this, of course, assumes that a is less than 1, because if it weren't, well, then what's this thing? That is, I have to worry about the fact that if I have an infinite number of waiting positions, then I have a stable solution only if the offered load is less than 1 or less. All right, so these two results are the same. This gives me the loss probability in terms of the sum of the tail probabilities for the case in which you have an infinite number of waiting positions. And this one gives it in the reverse. Now, the reason for this, the reason I want to investigate this, is that a common approximation, this is what people commonly assume. They say, okay, I want to solve this problem, but I can't. It's too hard because I have only a finite number of waiting positions. So what I will do is I will assume I have an infinite number of waiting positions, and then I will simply sum those probabilities from n plus 1 to infinity, and I'll call that the loss probability. I know it's not exactly the same thing, but I say the probability that an arriving customer finds a system in state n plus 1 and is lost if the block customers are cleared, or if the overflow customers are cleared, should be roughly the same as if I let them wait around, the probability that the number present would be more than the number of waiting positions. So it's sort of a rough approximation. And I want to do some numerical calculations to compare the exact result with that approximation. Okay, so part number 3, this is part number 2. So 3 says calculate Pj for 2 cases to be able to make these calculations. Now Pj is the probability that during a service time you have exactly j arrivals. So by definition, that's this. The integral from 0 to infinity of lambda t to the j over j factorial e to the minus lambda t dh of t. H is the distribution function of service times. And the way you calculate these probabilities is there's a recursive relationship, a relationship that allows you to calculate each one in terms of the others. We already did that. And in order to do that, you have to, in those equations are these probabilities. So these may be hard or easy to calculate in any particular case, but whatever they are, once they're specified, then the calculation is the same. So you could write a program that calculates these pi's according to the formulas given in the book, all you would do for any particular case is specialize it by telling what the service time distribution function is, and then that tells you what these little PJs are. Now, in the case, there are 2 cases we're interested in here, the 2 easiest cases. If the service times are constant, then of course the probability of j arrivals during a service time is just the Poisson probability. If the service times are exponential, then what I would do is I would substitute for this thing, well, let's see it, I'd substitute for dh of t, mu e to the minus mu t dt. So that's in the exponential case, exponential service times. And then then you just evaluate the integral. However, you don't have to evaluate the integral. You can do it by common sense or intuition, maybe is a better way to say it. Because the question here is, suppose that I have a service time. So this is the service time. And I want to find the probability that during that service time, I have exactly j arrivals. Now, because of the Markov property of the exponential distribution, I could make the following argument. I could say, well, I'm going to have a race between the service time and the inter-arrival time. And in order for there to be exactly j arrivals before the service time ends, what that means is that first I'll have the race, and the race must be won by the arrival. And then I'll have another race. Now I can start the service time again from the beginning, because by the Markov property, if the service time has been interrupted, the remaining service time is independent of the elapsed service time. So the probability that the arrival occurs before the service time ends is equal to lambda over lambda plus mu. Okay, we've already done that. We have a race between two exponentials, and the probability that the race is won by a particular one is the ratio of its rate to the sum of the rates. So we did that a long time ago. Okay, so the probability that I have an arrival before the service time ends is lambda over lambda plus mu. And then the probability that the next arrival will occur before the service time ends is the same, and so forth for each of them, up through j of them. So this is the probability that in j such races that the inter-arrival time wins. And then the service time must win the next race, because if it doesn't, then there will be more than j arrivals. The probability the service time wins this last race is mu over lambda plus mu. Of course, that's a geometric distribution. So the point here is that this integral is easy to evaluate by intuition if you take into account the Markov property. Okay, so in any event, we know what Pj is. There it is. So I have a formula for that in both cases, whether it's constant or whether it's exponential. Okay, different formula, but nevertheless explicit formula. Okay, now, question says, use these p's, these guys, to calculate pi sub n plus 1 when n is equal to 28 waiting positions and a equals 0.9 Erlangs. Okay, so let me get rid of this. Now that's a bizarre number to pick, but I picked it because it was in a book somewhere, and in that book they had actually done some calculations, so I had to check as to what the answers would turn out to be. So that's why I picked that one. So we want to calculate is pi sub n plus 1 when n is equal to 28, which means pi sub n plus 1 would be pi sub 29. Actually, the author in that book made a mistake because he meant to have 30 waiting positions, or a capacity of 30, but he got confused between the n and the n plus 1, and he made it 29, which means that for our notation, n is equal to 28, but that's neither here nor there. Okay, so also we want to take a equals 0.9. So that's 0.9 Erlangs. And then what it asks you to do is to make the calculation. So I'm asking people to make that calculation so I can check the numbers and see whether it's the same as what this other person has in his book. Okay, so here's the pi sub n plus 1. And it asks you to do it two ways. One way from this exercise, and the other way from another exercise. And that exercise is one in which the pi's were calculated directly for the case of exponential service times. So that's easy. That's just rate up equals rate down. That's just a check. Okay, so when you do it, there's two cases. There's MM1, exponential service times, and there's MD1, constant service times. For exponential service times, this turns out to be 0.00499186, and so on. Okay, I'm just putting down a number because I'm gonna think about that in a moment. All right, now this is from the exercise, and here in the second part, this is for MM1. Okay, so this one is for MG1 MM1K, and this is for MM1K. So MM, of course, we don't need any of this theory. It's easy. So when you make the calculation for MM1, then you will find that the answer is the same as that, so that's checked. That checks. That makes things consistent. So these two numbers are going to be exactly the same. In this case, for MD1, you can't do this way by rate up equals rate down, because you don't have everything exponential, but you could still do use the formulas that we have up here. And in that case, the answer turns out to be 0.00028,325. Okay, so the first thing to notice is that here the answer is has 2 zeros, and here the answer has 3 zeros preceding the first non-zero value. And this one is roughly twice as large as this one, which means that the probability of blocking is about 20 times larger here than it is here. So that's the effect of the exponential service time. The variability of the service times from exponential, which is completely random, to deterministic, which has no randomness at all, produces a factor of 20 in the fraction of customers who are lost for these values of the parameters. Okay, so obviously that the service time is important. Okay, now let's go to part 5. It says, let n be the smallest number of waiting positions such that pi sub n plus 1 is less than or equal to 10 to the minus 3. So in other words, what I want to do now is I want to find how many waiting positions I have to provide for various values of the offered load A, and there are going to be 2 cases, such that the fraction of customers who are lost will be less than 1 in 1,000. That's a reasonable way that you would engineer a buffer. Okay, so here is the table that you're asked to fill in. First of all, we're going to look at MM1K. So this is the case where we actually don't need all this theory because we have exponential service times. And then we'll look at the case in which we do need all the theory, MD1K. Okay, so those are the 2 different models. And then we're going to do 2 different values for A. A is equal to 0.9 Erlangs, and A is equal to 1.1 Erlangs. Now, if we had an infinite number of waiting positions, then of course in this case you wouldn't have stability because you would have an offered load greater than 1 Erlang. However, if you have a finite number of waiting positions, then there are no convergence problems, and you can take any value of A you want. These 2 values of A are pretty close to each other, 0.9 Erlangs and 1.1 Erlang. But of course, it's critical with an infinite number of waiting positions because this one leads to a stable distribution, and this one leads to an infinite queue, an unstable distribution, or no distribution, whatever you want to call it. Okay, so the first question is, what about n? Okay, now, by arithmetic, that is, you write a program that solves these equations, and you vary n, and you find out that when n is equal to 43 in this case, 43 buffers, then the fraction of customers lost is less than 1 in 1,000, and when it's equal to 42, then it's more than 1 in 1,000. So 43 is the number of buffers you need. Okay, what's pi n plus 1? Again, you have 2 ways to compute this for MM1 because you compute it using rate up equals rate down like in the first chapter, or you can compute it from the algorithm we have that works in general. You get the same answer because we already verified that here. Okay, now you know that the answer has got to be less than 10 to the minus 3 as a check. So when you compute it, this turns out to be 0.000978. So that's slightly less than 0.000978. 0.001. Okay, now here's the interesting part. What's pi sub n plus 1 of infinity? In other words, suppose that instead of getting the exact answer, I got the answer for the case of an infinite number of waiting positions, and then simply summed the probabilities for all states greater than n, and took that as an approximation for the loss. And the answer turns out then to be 0.0097. And that can be obtained in this case either by working this out, because you can actually get the state probability if you have exponential service times, or by plugging this value into this formula and putting in a equals 0.9, and then you get that value. Okay, so notice the way these numbers work out, that there are 2 decimal places in front of the 9, 3 decimal places in front of the 9. In fact, what that means is, although I didn't plan it this way, it just worked out, that this one is 10 times as large as this one. So in other words, if you made the common sense approximation, you would be off by a factor of 10. Of course, another way to look at it is you're only off by about 0.0009, right? It's a little tiny number, but it's a huge fraction. Okay, so in other words, it's not a good approximation because the ratio of this to this is 1 to 10. Okay, now let's look at the MD one. In this case, it turns out solving the same problem. Okay, so I'm solving the same problem except that I'm using the PJs for constant service time instead of exponential service time. And it turns out that the number of positions I need, waiting positions, is 22, which is about half of what I needed before. Of course, that's in a sense not surprising because if you look over here, the probability of blocking of loss was 20 times higher for exponential service times than it was for constant service times for the fixed parameters. So again, you see the same effect, which is that if I have less variability in the service requirement, then I need a smaller number of buffers to ensure the same amount of loss. So it turns out to be about 2 to 1. In this case, of course, again, the answer should be slightly less than 10 to the minus 3. And if you work it out, it's 0.000988, which is just about the same as that. And if you work out this case, now this case for MD1 cannot be worked out by finding the state probabilities and summing them up because you don't know what those are. Although, of course, you could do it numerically to any desired degree of accuracy. But if you plug into this formula, then you will find out that the answer is 0.0098, which once again is just about 10 times as large as that. So you have the same relative value between the truncated value and the tail probabilities, about 10 to 1. So in other words, this is not a good approximation. Of course, it would be better if the value of A were small, but 0.9 is fairly near the critical point. Okay, now suppose you used A equals 1.1, then what would happen? Okay, now that's interesting because remember that when A is equal to 1.1, well, first of all, this doesn't apply anymore because that's only for A less than 1. Because if A is greater than 1, then these probabilities don't exist. Okay, so it turns out that if you were to run this program with A equals 1.1 and do it until, for the first time, you had the probability of overflow being less than 10 to the minus 3, it would turn out that this is going to be a huge number. It turns out to be, I'll just write greater than 1,000, because the arithmetic starts to fall apart there. So it's a huge number. Okay, now in that case, what is pi sub n plus 1? And it turns out if you do it, you'll find the value looks like this. It turns out to be 0.09 with the 09 repeated over and over again, which of course you recognize is the same thing as 1 divided by 11. Okay, now suppose I did the same thing for MD1. Well, once again, I get a huge number of waiting positions here required, let's say greater than 1,000. And if I calculated for whatever this is, it doesn't matter whether it's 1,000, 1,500, 2,000, it turns out that for large values of this, large finite values, no matter how large, that this answer always turns out to be 0.090909 and so forth, or in other words, it turns out to be 1/11. Okay, so these answers are the same, even though otherwise the answers are much different between MM1 and MD1. Okay, what about the this value here? Well, if I had an infinite number of waiting positions, then of course we know that the that this probability would be 1. If I sum the probability of being in state n plus 1 or higher, we know that the probability is 0, in fact, for every finite n, and would be, we think, 1 when n goes to infinity. But of course, you can't calculate that. That's only mathematics. If you actually try to calculate it, well, what you would find is your answer would be very close to 1. But again, you'd probably run into numerical problems. So a question is, what's going on here? How come you always get 1/11? Okay, so what you want to know is this. You say, well, look, I'm going to let this n get very large. So in a sense, I'm letting this n go to infinity because if I have 1,000, 2,000 or so of these guys, that's for all practical purposes infinity. So if I let this get very large but still let it be finite, or let it go to infinity, what does that mean? That's to say that if I have an infinite number of waiting positions, what fraction of the arriving customers are going to overflow that infinite number of waiting positions? Because we know with probability 1, the queue length is going to be infinite. So what we really need to do here, what this is really asking is, suppose I take the limit as n plus 1 as the capacity goes to infinity of pi sub n plus 1. Of course, if a is less than 1, then this is going to go to 0. So it's going to be 0 if the offered load is less than 1 Erlang. Suppose the offered load is greater than or equal to 1 Erlang. Then it turns out that the answer is a minus 1 over a, independent of the distribution of the service time. Doesn't matter whether it's m or d or anything else. And why is this? Okay, if you think about it, what this says is, what fraction of the customers are going to overflow my, my waiting positions as the number of waiting positions goes to infinity? And so you say, well, think about it a minute. If the number of waiting positions goes to infinity, then for all practical purposes, in a sense, you've got an infinite waiting position queue, which means that the probability that the server is busy is 1, and therefore you're carrying 1 Erlang of traffic. So if you're offering a Erlangs of traffic, and you're carrying 1 Erlang of traffic because the server is always busy, then a minus 1 Erlangs is the number of Erlangs that overflow the waiting positions. So if I divide the number of Erlangs that overflow the waiting positions by the number that's offered, then I should have the fraction of customers that overflow the buffer. And so that's the answer. And that, in fact, would give me, in this case, if a is equal to 1.1, then this would be 1.1 minus 1, which would be 0.1 over 1.1, which is 1 over 11, which is 0.090909. So everything works. In fact, you can draw a graph. Looks like this. Okay, I'm drawing a graph of, here is the probability of overflowing my n waiting positions. It's a fraction of customers who were lost. And here is the number of waiting positions. Well, actually, it's the capacity. Capacity is n plus 1, number of waiting positions is n. So the smallest value for the capacity is 1. And then you could have 2 and 3 and 4 and so forth. Now what this says is that as the capacity goes to infinity for, in our case, A equals 1.1, as the capacity goes to infinity, then the fraction of customers lost would approach this value 1/11. So that's the asymptote. Now, when n is equal to 0, meaning the capacity is 1, that means that we have one server and no waiting positions. So that's an Erlang loss system. And in that case, we know that the fraction lost is equal to A over 1 plus A, independent of the distribution of the service times. So A over 1 plus A in our case, that's 1.1 over 2.1. That's about 56%, 52%. So let's say that's it there. So what that means is that, well, it would be it here for a capacity of size 1, no waiting positions. So the loss probability would be 52% if instead of having no waiting positions, I added 1, then it would drop to something smaller than that. And if I added 2, it would drop to something smaller than that, and so forth. So for each additional waiting position, the fraction of customers that are lost would go down. But in the limit, as the number of waiting positions goes to infinity, the loss would stabilize out at 1/11, or A over A minus 1 over A. So this is interesting because from a practical point of view in communications, the kind of questions you want to ask are, how many buffer positions should I provide? And then once I provide that number, what happens? What goes on? And in some cases, you can approximate it by assuming the number of waiting positions is infinite, but you got to be careful as these results show. So this is very practical stuff. And I've told you everything except actually writing the program and deriving the formulas that is deriving this. But this is easy once you do the stuff that's in the book and look in the solutions manual. So from our point of view, I don't think it makes sense in the context of this course to assign this as a homework problem. It's just as worthwhile just to discuss what the answers are. Okay, any questions about that? Okay, so that finishes up MG1K, at least as much as I want to do, although there's a lot more that could be done. Okay, so now I want to start on the next section. So I'm going to skip some stuff, although I may go back to it later. And I'm going to start talking about queue served in cyclic order. So I want to get to these polling models because that's the hot area of research right now. At least for me, that's what I'm doing. So our objective is to be able to look at models like this. We have a bunch of stations, and we have a server, and the server serves these stations in cyclic order. So at each station, customers arrive and queue up like that. And the server serves the station, then it switches to the next one, and so forth. So we could take the point of view that if we concentrate on one station, call this the target station, then when the server is serving all the other guys, he's on vacation. So that means that if I can figure out how long it takes to go around, all I have to do is hook that to what would happen if the rest of the guys weren't there. Because the vacation decomposition says that the waiting time for somebody in this queue is what his waiting time would be if there were no vacations. That is, if all these other queues didn't exist, plus a piece that has to do only with the vacations and nothing to do with that queue. So that's going to be the strategy. Now, in order to do that, I'm going to start with the simplest possible case, just to show you the kind of thing that goes on, and then we'll make things more complicated. Did I see a question there? Do you have a question? Okay. So the example I want to look at is where I'm going to simplify it in two ways. First of all, there's going to be only two queues. So the server is going to switch back and forth between two queues instead of n queues. And second of all, I'm going to make it symmetric. That's a big simplification. That is, I'm going to assume that each queue has the same arrival rate lambda, and that the service time distribution is the same in each queue. It doesn't matter what it is, but it's the same. And what that means is that I don't then have to differentiate when I write my equations as to whether the server is at this queue or this queue, because statistically they're the same. Okay, so this is the simplest case, and so I'm going to start with the equation 13.1. And this stuff is really amazing, as you'll see in a moment. Everything works out so neatly that it's unbelievable, at least if I don't make a mistake. This is on page 263. So suppose I let P of k be the probability that at a switch point, all right, now we've got to define some new things here. I want to analyze this system, and the old way to analyze it would be to say, well, what I'm going to do is I'm going to embed a chain at the instance at which customers complete service. Now, I could handle that in the case where there's only two queues, but in the general case, it's too complicated. And so I've got to somehow or other reduce my dimensionality. So what I'm going to do is I'm going to define a switch point as the instant at which the server switches from one queue to the next. And then I'm going to calculate, I'm going to let pk be the probability, in this case, that when I switch from one queue to the next queue, there are k customers waiting in the queue that I switched to. Now, it's not clear that that's enough information to give you anything out, because I want to know, in the end, how long a customer waits. And it's not clear that I can get that information if all I know is the state of the system when the server switches. However, if you remember when we did MG1 by embedding a chain at the service completion epochs, it wasn't clear that we would be able to get waiting time information out of that, but we were. So right now we'll go on faith in saying, well, let's look at the server at the switch points, because if you do that, at least we can solve the problem, and then that's a step, and then let's see if we can solve that problem, whether then we can go from there to waiting times. So right now the question is, I'm going to define this distribution as being, this is the probability that when I switch from one queue to the next, there are k customers waiting in that queue that I switched to. And this is in equilibrium. We're assuming statistical equilibrium. And we're also assuming exhausted service. By exhausted service, what I mean is that the server does not switch until the queue is empty. And then when it does switch, it works until that queue is empty. Okay, that's exhausted service. So let me write down that name. Exhaustive service. There are other assumptions you can make. Of course, they lead to other models. But this is the most basic model. Okay, so what's the probability that when I switch from this queue, there will be exactly k customers waiting in that queue? Now, we know that when I switch from here, the number that's waiting here must be 0 because of exhausted service. So I don't need an index to tell me what the state of that queue is. I know that at a switch point, the queue that I'm switching from is empty. and the other queue has a certain number, has k customers waiting with probability pk. Okay, now the way I'll argue that is I'll say, well, the probability that there are k when I switch to here is, first of all, the probability that there were j when I originally switched to here. And if during the time I spent serving those j customers and all of their descendants, exactly k arrived here. Okay, because if when I started working here, there were j, what I know is there was nobody here because I don't leave this queue until it's empty. So there will be k here if there were j here when I last left this guy, and during the time I spend here, exactly k arrived to here. Okay, so pj is the probability that when I started serving this queue at the previous switch point, there were exactly j, where we're going to assume, obviously I'm going to sum over something, and I'm going to assume that j is at least 1. And I'm going to take the 0th case separately. Okay, now, suppose there were j customers here. How much time do I spend here? Well, the answer is a j busy period, because this is now an MG1 queue in which when the service starts, there are j customers present. So if I call the distribution function of the j busy period b sub j of t, then dbj of t is the probability that the length of time I spend here, the time to serve the original j customers plus all of their descendants, is exactly t. And during that time, if there were to be k when I switch there, exactly k must arrive during that time of length t. And the probability of that is lambda t to the k over k factorial e to the minus lambda t integrated as t runs from 0 to infinity. Now, that's if at the last switch point, the number of customers in the other queue was j. But suppose at the last switch point, the number of customers in the other queue was 0. All right, now we got to worry about this, because in our model, when we switch from one queue to the next, you switch instantaneously. That is, there's no travel time for the server to get from here to here, but there's a 0 travel time, or what's called a 0 switchover time. So that means that if I switch to a queue and I find it empty, then I immediately switch to the next queue, but it's empty, and then the next queue and it's empty, and so forth. So what happens is that I will go into this infinite fibrillation. I'll just be going back and forth, and I'll go through an infinite number of cycles in a finite time. So this is a conceptual difficulty, but our particular way of looking at it avoids that problem. Okay, so what I'm going to say is that if the system is empty at a switch point, then the server does nothing. It just sits there. And then as soon as somebody arrives, no matter which queue it arrives to, the server jumps to that queue in 0 time. So I could imagine that it stays at the original queue. And if the next arrival occurs at that queue, then the server switches to it immediately and starts to work. And if the customer arrives to the other queue, then the server switches to it immediately and starts to work. So that's my model. Okay, now the question is to how I relate that to the case in which I require, say, that there be positive times from here to here. That's an interesting problem, and one that we'll get to. Okay, but in the 0 switchover time model, if the system is empty, then instead of having the server make an infinite number of cycles in a finite time, what I simply do is say the server stops. And then whenever a customer arrives, say here, the server immediately goes to that guy and begins service on him. So the server is sort of in limbo when the system is empty. Otherwise, I've got the problem of the fact, well, look what would happen if I would assume that it takes a certain length of time to go from here to here. If I could solve that model and then let that time go to 0, would I get this model? I don't know, because as the time goes to 0, that means that the server switches infinitely fast, and it's not clear what happens in the limit. The whole thing falls apart. So in fact, that was an area of research that was underway for about 25 years, and it's finally now people are just beginning to understand it. That is the connection between the 0 switchover time model and the non-zero switchover time model. There was always seemed to be this pole at separating those two models. Okay, now this says the probability that there are k in the queue that I switch to is equal to this if at the last switch point the system had j customers present, plus here's the probability that at the last switch point the system was empty. If the system was empty, then the server does nothing until a customer arrives, and as soon as it arrives, it switches to that queue, and then the next switch point will be registered when it switches from that queue to the next. And so if that happens, then the probability that there will be k in the next queue when I again switch is going to be given by the probability that during a busy period that began with one customer, in other words, an ordinary busy period, there are exactly k arrivals. Okay, so these are my equations. So let me just repeat the argument and then say what the strategy is going to be, and then we'll start from here next time. Okay, right now, even though if you buy these equations, it still looks hopeless, because remember, you're integrating with respect to the distribution function of a busy period, which is extremely complicated. Okay, but the argument I made at the time we discussed the busy period was, don't worry about it, because it turns out it doesn't matter. That all of the mathematics, all the difficulty goes away. So that's what's really amazing here. Okay, so what does this say? What's the probability that when I switch to a queue, there are k customers waiting there? It's the probability that at the last switch point, there were j waiting in the queue I switched to, where j is at least 1, times the probability that during the j busy period, which is the length of time I spend serving those j customers and all their descendants, exactly k new customers arrive to the queue that I've just switched to. Plus the probability that when I last switched, at the last switch point, the system was empty, in which case, when I finally switch again to the next queue, there will be k waiting if the, okay, I kind of said that wrong. This is the probability that when I finish serving the queue that I've been working on, that the whole system is empty. And in that case, the server just stops and does nothing, and then it immediately jumps to whatever queue the first arrival occurs at. And then the next switch point is registered when I switch from that queue. What's the probability that when I switch from that queue, there will be k people waiting in the next queue? The answer is, well, it's the probability that during that busy period generated by that one customer that ended the idle time, exactly k new customers arrive to the queue in question. And I don't have to differentiate the queues because remember, I've got symmetry here, symmetric queues. So that's a major simplification, which we're going to have to do away with when we get to the real thing. In any event, those are my equations, and now the question is, what can I do with it? How can I solve those equations? So the strategy is going to be that I'm going to form generating functions and then do some arithmetic. And as you've already seen, when you do that kind of stuff, lots of things simplify. And as you'll see, it'll all simplify, and we'll actually be able to get a solution for this without very much work, because of surprising relationships that just happen to fit together like that. Okay, so that's where we'll start next time, and the objective is to get to this model right here, the case where the number of queues is more than 2, and the parameters for each queue are different. It's not symmetric. And then to connect that, in which the switchover times are 0, to the case in which they're not 0, so we've solved everything. Well, almost everything. Okay, so are there any questions before we quit? Okay.